Welcome to the next video in discrete math series. In this video, we will talk about equivalence relation. If you are new to the channel, I would suggest you to subscribe the channel so that you can get good quality video content. Now, what is the definition of an equivalence relation? A relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. In case if you do not know what is reflexive, symmetric, and transitive relation, I would suggest you to watch the previous videos in this playlist. So I hope the definition is clear to you that for a relation to be an equivalence relation, it should satisfy three characteristics. It should be reflexive, it should be symmetric, and it should be transitive. So to understand it better, let us look at some of the examples which I have written over here. So start with the first example. So if you see the first example here, it is going to have 0, 0, 1, 1, 2, 2, and 3, 3. So all elements of AA type are there, because in A we have 0, 1, 2, and 3. So all such AA type elements are there. So this relation is a reflexive relation. So there is no confusion here. It is certainly symmetric, because if A and B are not equal and we don't have any such element where A and B are not equal, so AB type element is not present. So we don't care whether BA is present or not. So it is certainly symmetric as well. And it is transitive also, because for a relation to be transitive, what is the requirement? That if AB is in the relation R and BC is in R, then AC should be in R. That is important. You need to realize this, that if AB is in R and BC is in R, if these two requirements are there or met, then we look for AC. But here we don't have any such option, that because we have just 0, 0, 1, 1, 2, 2, 3, 3. So this relation is transitive as well, right? So because it has all the three properties of an equivalence relation, so this relation is an equivalence relation. Now let us look at the second example. So second example, if I see here, we have 0, 0, we have 2, 2, but we don't have 1, 1. 1, 1 element is not present, and 3, 3 element is also not present. So it means what? That it is not reflexive. And the moment we realize that it is not reflexive, we are certain that this is not an equivalence relation, right? But just for the sake of understanding purpose, let us check about other characteristic also. The question is already answered that this is not an equivalence relation, because the very first property of being the relation to be reflexive is not being satisfied. Now whether it is symmetric, so let us see. We have 0, 2 and we also have 2, 0. So for this, that requirement is fulfilled. If we have 2, 3, then we also have 3, 2. So it is symmetric, right? What about transitive? So for transitive, we need to check. So let us look at this element. We have element 0, 2 is given. If I call this relation R, let me call this relation R. So if 0, 2 is in R, and we also notice that 2, 3 is in R. 0, 2 is in R, and 2, 3 is also in R. You can see we have 0, 2 and we have 2, 3. So if I combine both of them, then this should imply that 0, 3 should be in R. For the relation to be transitive, since 0, 2 is in R and 2, 3 is in R, then 0, 3 should be in R. But we don't have 0, 3 element here. So 0, 3 is not in R. This does not imply that 0, 3 is in R. So that is why this is not transitive, right? So it was not reflexive also, it is not transitive also. It was symmetric, but since two properties are not met, then it is not an equivalence relation, right? So I mean here this not imply sign is slightly mathematically not precise. So if 0, 2 is in R and 2, 3 is in R, and 0, 3 is not in R, so it is not transitive. Let us look at this third example, C example. So we have 0, 0, we have 1, 1, we have 2, 2, we have 3, 3. So it is reflexive because for all the four elements 1, 0, 1 and 2 and 3, we have 0, 0, 1, 1, 2, 2 and 3, 3. So reflexive is there. Whether it is symmetric, so we have 1, 2 and we also have 2, 1. So it is symmetric as well. There is no other AB type of element ordered pair is there. Now what about transitive relation? And just to understand transitive relation, this will be an important example as well. So you see 0, 0 is there and there is no other element which is starting at 0, so we don't have to check anything further. Now if I take 1, 1, here we have 1, 2. So 1, 1 and 1, 2 is present, so 1, 2 is also present, right? 1, 1, so only one element is ending with 1 and starting with 1, so this pair I already have taken care. Now take 1, 2. So if I take 1, 2 and 2, 1, then 1, 1 should be there. So 1, 1 is present, right? Now 1, 2 is there and 2, 2 is there. So 1, 2 should be there. So that is also present. Now there is no other element which is starting with 2. So I am done with this part also. Now take 2, 1. So 2, 1 is here and 1, 1 is here. So 2, 1 should be there. So that's also correct. 2, 1 is here and 1, 2 is here. So 2, 2 should be there. So that is also present. So that's done. Now move to the next element 2, 2. So 2, 2 is there and 2, 1 is there. So 2, 1 should be there. So that is present. 2, 2 is there and there is no other element starting at 2. So that requirement is okay. And finally we have 3, 3, but there is no such element like 3, something. So this is a transitive relation as well. If you want to understand, I would like to do one more thing for I will prefer drawing even the what you call the directed graph representation, because we have seen it in earlier videos. So let us try to do that. So we have 0 here, we have 1 here, we have 2 here, we have 3 here. So what are the elements 0, 0, that ordered pair is there. We have 1, 1, so that loop is present, this loop is present, this loop is present, 2, 2 loop is present, 3, 3 loop is present, right? And other than that we have 1, 2, so there is a directed edge between 1 to 2, and since it is symmetric, so there is a directed edge between 2 to 1 as well. And now you see that there is no such confusion that if there is an edge between A and B and C and there is no edge between A and C. So certainly this is a transitive relation. So this is transitive as well, and since it is transitive as well, so this relation is an equivalence relation. Now there are two more examples which I leave for you to verify whether these are equivalence relation or not. I'm going to take this interesting example of congruence modulo M. And before I take this example, I hope you understand that what is the meaning of A is congruent to B modulo M. If you don't know, let me explain it quickly. So we say that A is congruent to B modulo M if M divides A minus B. M divides A minus B, right? Now we have to check that on the set of integers like Z, whether this is an equivalence relation or not. So let us check it one by one. So first we check the reflexive property. So what is the reflexive property? That we know that M divides A minus A for all element A in the set of integers, right? Because A minus A is equal to 0, so if you take any element and subtract it from itself, you will get 0. So M will certainly divide, and this symbol, like here if I write A divides B, so this is how the divide symbol is written. So basically this is true. So this is a reflexive relation. This is a reflexive relation because A is congruent to A modulo M for all A in the set of integer. There is no doubt about that. What about symmetric property? So for symmetric property, what is the requirement? So suppose I say that A is congruent to B modulo M. So if A is congruent to B modulo M, this implies what? This implies that M divides A minus B. If M divides A minus B, means A minus B can be written as some integer k times m, where k belongs to set of integer, right? Now if a minus b can be written as k times m, I hope this is obvious. If I say that 4 divides 20, so it means what? That 20 can be written as 4 into some integer 5. So this is what I am doing here. And if a minus b is equal to k into m, then what will be b minus a? B minus a will be minus k into m, right? And since k is an integer, minus k is also an integer. So we conclude what? We conclude that b is congruent to a modulo m. Yes or no? Because if you divide b minus a by m, you will get minus k as the quotient. So if a is congruent to b modulo m, then b is congruent to a modulo m. So it is symmetric relation as well. It is symmetric. Now let us move to the next page and try to show that it is transitive as well. I have something else written over here. You can ignore it for a moment. So for checking the transitive property, what is the requirement? So see, if I say a is related to b, means a is congruent to b modulo m, right? That is how the relation is defined. That if a comma b belongs to R, means a is congruent to b modulo m. And b is congruent to c modulo m, right? Suppose it is there that let a is congruent to b modulo m and b is congruent to c modulo m. So since a is congruent to b modulo m, it means what? It means that m divides a minus b. And if m divides a minus b, means a minus b can be written as some integer k1 times m, where k1 belongs to the set of integer. And b is congruent to c modulo m, it means that we can write that m divides b minus c. So b minus c can be written as what? It can be written as k2, which is an integer, times m, where k2 belongs to the set of integer. Now we have to show that a is congruent to c modulo m. So let us write a minus c. So how can we write a minus c? We can write a minus c as a minus b plus b minus c. And a minus b is k1 into m. So I write a minus b as k1 into m. And b minus c is k2 into m. So I write it k2 into m. So what did I get? I got that a minus c is equal to k1 plus k2 into m. And since k1 is an integer and k2 is an integer, so k1 plus k2 is also an integer, where I can write that k3 is equal to k1 plus k2, and k3 belongs to z. Okay. So this implies that a is congruent to c modulo m. Okay. So we have shown that if a is congruent to b modulo m and b is congruent to c modulo m, then a is also congruent to c modulo m. So this is transitive property, means this relation is satisfying the transitive property as well. So we have seen in the previous page that it was reflexive and symmetric. Now in this we are looking at this and realize that it is transitive also. So this relation a is congruent to b modulo m, which was defined on the set of integer z, means z was an infinite set, or is an infinite set rather. So on this infinite set, this relation is an equivalence relation. I hope you got this point. In case if you have not understood, please put your query in the comment section, so that I can understand that where you have got into trouble, right? Now the next thing that actually I wanted to discuss was partition of a set on this page. So let us move to the next page to discuss about the partition of the set and other aspects of equivalence relation. So what is partition of a set is? You can read this definition and then I will explain. A partition of a set S is a collection of disjoint non-empty subset of S that have S as their union. In other words, the collection AI forms a partition of set S if and only if AI is non-empty for all I, and AI intersection AJ is equal to empty set whenever I and J are not equal, and the union of all the AIs must be equal to S. So to understand this, I take a simple example. Suppose I take a set S which has the elements like 1, 2, 3, 4, 5, 6. And I write a collection of subsets of the set S. So let us write A1 which contain 1, 2, A2 which contains the element 3, 4 and 5, and let us write the set A3, subset A3, which contains the element 6, right? Now the first thing that you need to notice that each of these are non-empty subsets. Why they are non-empty? Because each of them have at least one element. Okay. Now the next thing I want you to notice is that if you take the union, means if you take the union of A1, A2 and A3, you get S, because 1, 2, then 3, 4, 5 and then 6, so you get the whole set S. And along with that, you also notice that if you take the intersection of any two of them, means if you take the intersection of A1 and A2, you get an empty set. If you take the intersection of A2 and A3, then also you get an empty set. And if you take the intersection of A3 and A1, then also you get an empty set. So it means that the requirement for the collection, this collection of subsets to be a partition is fulfilled. What was the first requirement? That each of them should be non-empty. Second requirement, their union should be the whole set S. And the third requirement is that their intersection must be equal to empty sets. And that should be true for all possible pair of subsets of S, right? So this is how we define the partition. Let me give you one example which is not a partition, so that you are clear about this. So suppose I take another set, let me take this set B, and suppose I take it has elements like A, B, C, D, E, F and G, and I write a collection of it. Suppose I write the collection A1 which contains element like A, B, C. We have another subset which contains element like C, D, E, and I write A3 where I write E, F and G. So first requirement, that each of the subsets must be non-empty, that is okay, fulfilled. Second requirement, that if I take union of A1, union A2, union A3, that should be the whole set, which is B in this case. So that is also correct, because A, B and C is there, C is there, and D, E and F, G all are there. But you notice here that A1 intersection A2 is actually not empty, because you have a common element C. You also note that A2 intersection A3 also have a common element E. So if we have a common element between any two subsets, in that case we say that this is not a partition. Okay. Now let us talk about a very important idea of equivalence class, how the equivalence class is defined. So equivalence class is actually related to equivalence relation. Suppose we have a set A, and on this set A, suppose a relation R is defined. So the class of an element A, I'm talking about class of an element A, is either represented by this symbol or by this symbol, class of A. So it contains all those elements S which are related to A. Okay. So this is how the definition goes, that the class of A is the collection of all those elements S for which A is related to S, means A should be related to S, or I can write it that A comma S should belong to R. To understand this, let us take this example. This is a slightly good example, or maybe slightly engaging also, so you need to keep watching the video to understand it better. And this is an important example as well. So they are asking us to write all the equivalence classes for the congruence modulo 4. So let me first give you that what is the idea here, that suppose I take the set of integers, and on this set of integers I say that two elements A and B are related. A is related to B if A is congruent to B modulo 4. We have just seen what do you mean by modulo, right, in the this video itself. So if I have to write the equivalence classes for each of the elements, so I am starting with the first element, that is 0, and let us write the equivalence class of the element 0. Okay, now 0 is related to itself because 0 minus 0 is divisible by 4. We have seen this example that this is an equivalence relation, so 0 must be related to itself because equivalence relations are reflexive. Now 1 is not related to 0 because 1 minus 0 is 1 and it is not divisible by 4. 2 is not related to 0. 2 minus 0 is 2, which is not divisible by 4. 3 is not related to 0. 3 minus 0 is 3, which is not divisible by 4. But 4 is related to 0 because 4 minus 0 is equal to 4 and it is divisible by 4. 8 is related to 0. 12 is related to 0. I hope you have got the drift. Similarly, minus 4 is related to 0 because minus 4 minus 0 is minus 4 and it is divisible by 4. Minus 8 is also divisible by 4. Minus 12 is also divisible by 4, and so on. So this is the class of element 0 and it contains all the integers which are related with 0. Next element is 1. So let us write the class of 1. And I think now you are smart enough to understand that 1 certainly will be related to 1 because 1 minus 1 is divisible by 0. 1 minus 1 is, I made a mistake. 1 minus 1 is equal to 0, which is divisible by 4. So 1 must be here. Then what will be the next element? 5, because 5 minus 1 is 4 and it is divisible by 4. The next element will be 9 because 9 minus 1 is 8, which is divisible by 4. Next element will be 13 and so on. I hope you are getting the idea. What will be other elements, those negative elements? So the next element will be like minus 3. Why minus 3? Because 1 minus minus 3 is how much? 4. 1 minus minus 3 means 1 plus 3. That is equal to 4 and 4 is divisible by 4. Similarly, minus 7 because 1 minus minus 7 is 8, which is divisible by 4. Similarly, minus 11 and so on. Now I hope that the point in which the direction in which we are moving is clear to you. Now if I take the other element 2, then the equivalence class of 2 will contain 2, then 6, then 10 and then 14 and so on. And it will also contain element like minus 2, then minus 6, then minus 10 and so on, right? So I am writing it like this so that you understand. Otherwise I could have started from the left, but I am starting from the middle so that you understand it properly. Now what is the equivalence class of 3? So equivalence class of 3 will be 3, then 7, then 11, then 15 and so on. We are just adding 4 to each of the element, and then if I subtract 3 minus 4 I will get minus 1, then I will get minus 5, then I will get minus 9 and so on. So we have got 4 classes: class of 0, class of 1, class of 2, class of 3. Now I have a question for you. Please pause the video and answer this question, that what is the class of element 4, or what is the class of element 5 or 6 or 7. You realize that if you calculate the class of element 4, it will be nothing but the same class as class of 0. Because in the class of 4, if you try writing it, let me write it. Class of 4 will have what element? It will have 4, right? then 4 plus 4, 8, it will have 8, it will have 12, it will have 16, and so on, and it will have 4 minus 4, 0, then minus 4, and then minus 8, and then minus 12, and then so on. So did you notice one thing, that this class of 4 is same as class of 0? And now you are smart enough to guess that class of 5 will be same as class of 1. Class of 6 will be same as class of 2. Class of 7 will be same as class of 3. And again the class of 8 will be same as class of 0. So basically these are the only 4 disjoint classes possible. That is class of 0, class of 1, class of 2, and class of 3. And I hope you notice one important thing, that if I take the union, let me write here, if I take the union Z, let me make it slightly thicker. So if I take the union of all these classes, class of 0, union class of 1, union class of 2, union class of 3, then I am going to get the whole set of integer. You can see here 0, 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, and here also you have minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. So basically you will get the whole set of integer Z. Another important observation is that they are mutually disjoint. Means class of 0 does not have anything common between any of the other classes. Same true for class of 1, class of 2, and class of 3 as well. So we have noticed one very important point here, and that important point is that every equivalence relation partitions the set. This is an important point. Every equivalence relation partitions the set. So suppose I say that this is your set. So the equivalence relation R will do what? It will partition the set into disjoint equivalence classes. It may have certain number of partitions, and those partitions will be nothing but disjoint equivalence classes of elements. Okay. So if you have understood what is equivalence class, I think this theorem you should certainly try to write the proof that if R is an equivalence relation on the set A, then these statements are equivalent. So if A is related to B, then equivalence class of A will be equal to equivalence class of B. And that is what we have seen here. We have seen that 0 is related to 4. So equivalence class of 0 is equal to equivalence class of 4. 0 is related to 8. So equivalence class of 0 is also equal to equivalence class of 8. If you look at this 9, so 9 is related to 1 because 1 is congruent to 9 modulo 8. So equivalence class of 9 is equal to equivalence class of 1. So this property that if A is related to B, then equivalence class of A will be equal to equivalence class of B. And the third statement is that if A and B are related, then equivalence class of A intersection equivalent class of B must be non-empty, right? So these are the three equivalent statement. To write the proof, what you have to do, you have to show that A implies statement B, then you have to show that B statement implies statement C, and then you have to show that C statement implies statement A. And if you are able to show this, then you can conclude that these three statements are equivalent statement. I would suggest you to write the proof. It is very interesting and it will give you insight into that what is an equivalence relation and how the partition works. Okay. So now let us look at one theorem here. And this theorem I already have given you some hint about, that let R be an equivalence relation on a set S. The equivalence class of R forms a partition of S. Now you are clear about what do I mean by partition, right? And what do I mean by equivalence class and what is equivalence relation. Converse is also true, that conversely, given a partition of the set S, there is an equivalence relation R that has AI as its equivalence class. So basically the idea was that if you have any set A, and on this set A, if you have defined an equivalence relation, then this set A will be partitioned into different equivalence classes. Yes or no? So suppose I say that these are the different equivalence classes. This is one class, this is another class, this is third class, this is fourth class, this is fifth class. So there will be different disjoint equivalence classes of it. And if you take any such partition, this is basically a partition which is clear from the diagram that I have drawn, that if you combine all these partitions you get the whole set, and there is nothing common between them, right? Each of them are mutually disjoint. So I would suggest you to try writing the proof of this theorem. I am going to take this example to understand the things better. So suppose I have to generate, or rather I have to write an equivalence relation which I am defining on the set S given by this set S, which contains 6 elements. And suppose we have a partition that is given like A1, A2 and A3. This is the partition that is given. So based on this partition, if I have to write the equivalence relation, so what will be the equivalence relation? So let us understand it. As I told you that for every partition there will be a corresponding equivalence relation. So in every partition, what we are going to do, we are going to do that every element will be related to every other element. It means what? Let me rephrase my statement. Each of the element will be related to all the other elements. Like if I take the element 1, so element 1 will be related to 1, element 1 will be related to 2, element 1 will be related to 3. Similarly, if I take the element 2, so 2 will be related to 1, right? 2 will be related to 2 and 2 will be related to 3. Every element here will be related to all other elements of this partition. Similarly, if I take 3, 3 will be related to 1, 3 will be related to 2 and 3 will be related to 3. Now you look at this partition, or this class or this subset of the set S, which is basically the part of the partition. So here 4 will be related to all the 2 elements, means 4 will be related to 4 and 4 will be related to 5. And if I take 5, 5 will be related to 5 and 5 will also be related to 4. I missed to write this. 5 will be related to 4 and 5 will be related to 5. And finally 6. So 6 in this partition we have just one element. So 6 will be related to itself. I leave this for you to verify that this is an equivalence relation. This is guaranteed that this will be an equivalence relation. It is guaranteed by this theorem, because this theorem guarantees you that whenever given any set, if you are writing any partition of that set, then corresponding to that partition there will be an equivalence relation. Let us take one quick example. Suppose I take another set S which has just suppose 5 elements, 1, 2, 3, 4 and 5, and I write its partition like I write A1 is equal to having a 2 element 1, 2. Another partition, another is having 2 element 3, 4, and third partition, let me call it like having element 5, let me call it A3. So what will be the equivalence relation? If I have to write the equivalence relation in the partition, because this will act as disjoint equivalence classes, A1, A2 and A3 will be the different classes of the equivalence relation, right? So every element will be related to itself. 1 will be related to 1, 1 will be related to 2, 2 will be related to 1 and 2 will be related to 2. So these elements will be related among themselves, and these elements will not be related to any other element outside of that partition, right? Because of the result you have seen that if A is related to B, then class of A and class of B should be non-empty. Their intersection should be non-empty. Now if you take 3, 4, then 3 is related to 3, 3 is related to 4 and 4 is related to 3 and 4 is related to 4. and in the last class, this A3, we have just one element 5, so 5 is related to 5. So again I leave this for you to verify that both these relation, the relation R that I am representing through this and the relation R, both will be equivalence relation, right? You can verify the three properties, that it is reflexive, it is symmetric, and it is transitive, right? So that is all for this video. In this video I talked about what is equivalence relation. I talked about how the equivalence relation partitions the set into disjoint equivalence classes. We also understood that given any partition of a set, we can write a corresponding equivalence relation, right? So I believe you have understood the things. In case if you have understood the things, you should share this video with your friends also, and you like this video, share with your friends. And in case if you have any doubt related to what I have discussed in this video, you should put your doubt in the comment section so that I can understand that where the students possibly may face challenge. So thanks for watching, right? Have a very great day.